Okay, so it turns out that we could also express our mean as NP, N times P, for a binomial distribution, which in this case is going to be equal to 4 times 1/5, which is 4/5 or 0.8. So you see that these two things are the same. So we calculated our mean longhand and shorthand. And we wound up doing the same thing. I was a little confuzzled at the end because we miscalculated. I was like, oh no, they should have been the same. It would have been cool. I was trying to do something neat. All right. And the next thing that you know is that instead of calculating your standard deviation by doing the variance, where you have to do all those sums, you can instead, with a binomial distribution, you can use the formula that your standard deviation of your random variable x is going to be equal to n times p times 1 minus p. So that works for a binomial distribution. Of course, the formulas that I showed you for variance and mean of any random variable work for this as well. It's just that you can get a little shorthand version of it by using those. Okay. All right. So, it is important that we keep in mind this 10% condition. And we're going to use it quite often. When we start doing, we're going to have to check this quite a bit. As we go. So it's going to have to be the case that this equation must be true. So we have a sample size. So this is, we have an SRS of size n from a population and we're going to say population size capital N. So this has to be true in order to use a binomial distribution. So what this says is that our sample is large enough, all right? And we're going to be, when we start next semester, we'll be taking samples from populations and finding out information about those samples using all the tools that we've learned in this semester. But we're always going to have to check this condition if we're going to use binomial distribution. It's just brought up now. We're going to use it a lot in the future, but it's brought up now because we're in the portion where we're talking about binomial distribution. Okay. It just means that you have a sample size large enough. We're just checking that our sample size is large enough in proportion to our population size. All right. Okay. Your book has done a bunch, or one example where it says hiring discrimination, it just won't fly. We have to be careful. The whole point of the exercise is to tell you, be careful. You can only use binomial distribution if you're sampling without with replacement, right? If you're sampling without replacement, your distribution is no longer, or sorry, each individual probability is no longer independent. You know what I'm saying? Because the probabilities change as you take things out, right? So we're not going to get crazy about that. But just be careful when you're checking independence. So when you're doing your bins, if you're checking independence, whenever you're taking out, or whenever you're counting a success, if you take that success and take it out of your sample, then you change the probability. All right. All right. Let's talk about the geometric setting. Yay! All right. All right. So we were looking before at the difference between a binomial and a geometric setting is that in a binomial setting we're looking at the probability of getting a certain number of successes, right? In a geometric setting, we are looking at the probability of the first success, all right? So, and that definition is written down. Let's see, I'll try to write that. I guess I could write exactly what they say. So, what we're doing is performing independent trials. Using the same chance process. Wow, that's good handwriting. And record the number of trials. All right, so that's the difference, right? You're wanting to know k successes, what the probability is of getting k successes when you're doing a binomial, when you're looking at binomial distribution. When you're looking at the geometric setting or geometric distribution, you're wanting to know how many trials it takes before getting the first success. Cool, that's the big difference. All righty then. So. Let's do a problem. And let's give you a probability formula. So let's look at it. First, let's get the formula. Sorry, I was just I took that pause because this. So I just handed you the formula sheet, and this one's not on there. You'll notice, right? And I'll show you first. It's not on there because what we've got is it's P. The probability of Y equals K equals 1 minus P to the K minus 1, whoa, times P. Alright, and of course P is your probability of success. And K is your number of trials. So for instance, right, if you wanted to know the probability that you would get success on the third trial, you would like K equal 3, right, and so on. And so if you wanted to know the probability of success in the first 3 trials, you would have a probability of Y less than or equal to 3, right? And we'll actually work something right here. Let's look at Monopoly. Okay. All right, so we're going to talk about Monopoly, right? To get out of jail in Monopoly, what do you got to do?
Doubles.
Roll doubles. Don't you have to roll it in the first 3 chances, right? So let's look at Y. Our random variable Y will be the number of attempts it takes to roll as doubles one time. Number of attempts to roll doubles. Of course, one time, because that's all you care about, right? All right. All right. In this case, P is 1/6, right? Okay. What is the probability that it takes 3 turns? That would be the probability that Y is exactly equal to 3. Which, if we use our formula, we wind up with 1 minus 1/6 formula to the 3 minus 1 power times 1/6. Upon calculating that, you find that it is 0.116. But what is that? That's the probability that you do it on the 3rd try, right? That's the probability that you roll doubles, nope. You try to roll doubles, nope. And then the 3rd time, yes, you get it, right? Alright, so let's look then at the probability that it takes less than 3 times. Tries, right? Oh, more than 3 turns? That's annoying. Huh? I would rather do less than 3, or 3 or less, right? Huh? Yeah, the complement. Yeah. in order to do so, the book suggests that because it's more useful for learning is that you do the probability that it takes more than 3 times. But I'm pretty sure the rule is that you get out of jail, right? If you don't. Yeah. Oh, you still have to pay?
Yeah.
Okay. Okay. And is that on the first?
No, that's taking the long run.
Okay. So they probably actually used an expected value for that. You imagine, right? Huh? They had a bunch of stuff. I mean, you would have to use, like, in the long run, you would have to use an expected value for that.
Yeah.
So you'd have to find the probability distribution of landing on it, because the problem is that the probability of landing it on the first try is different than the probability of landing it on the first time or second time around, and so on. I would imagine you have to have a computer do that, or a lot of people working at the same time.
Yeah.
So, yes. That's the probability that you roll doubles on the third try. Yeah. And for this one, just as Ethan was saying, you would have to take the complement of p less than p probability y is less than or equal to 3, right? In order to find that it takes more than 3 times, which is kind of weird because you don't ever roll doubles more than 3 times in Monopoly. What I'm more interested in, really, which turns out to be 1 minus, I guess we could write it out. So this is going to be probability y equals 1 plus probability y equals 2 plus probability y equals 3. We do actually have a function for that on our calculator as well. So get up the cap. All right, so you may not have noticed that when we went to do our calculation for binomial, there is also a geometric cumulative distribution function. So we could have calculated y equals 3 with our with E geometric PDF, and we can also do less than or equal to 3 with our geometric CDF, where P is 1/6 and our X value is 3, and then and we get 0.421. Ooh. I wonder why. Okay, so 1 minus 0.42. And there it is. 0.57. Okay, but what I'm really more interested in is the probability that, which is not anything. I'm more interested in the probability that, isn't that what that is? The probability that it takes, that you can get it on less than 3 tries, right? So, probability that y is less than or equal to 3. But that's this part that we calculated already, right? So that is approximately. Alright. Perfect. I think this is a more interesting probability than the other one because that's the one you're looking for in the game. So really, I mean, the odds aren't terrible for you to actually roll doubles and get out. Within the time that it takes money, but good grief, it's just $50. Come on, you're playing Monopoly. You should be 1,000 there in Monopoly at least, right? Okay. The very last thing that we need to talk about with this is our mean or expected value for a geometric distribution. Yes. All right. So it turns out that our mean of a geometric random variable is the same thing, of course, right? It's our expected value of our random variable occurring, which is going to be 1 over p. Okay, but if we need to, so we really need to be able to interpret this, right? So an interpretation of this is the expected number of trials to get the, not good English, but to get the first success is 1 over p. So, if we put that into context, right? If we're rolling doubles, how many times should we roll it before we expect to actually get doubles, right? So, yeah, so that would be 1 over 1/6 or 6. So this actually tells us something very interesting. It tells us that if you're rolling 2 dice, you should expect to get doubles within the first 6 rolls. That's pretty logical stuff to me, this stuff. It makes sense. You can try it.
You got this?
Huh? I'm not sure. I should. I used to have some. I was borrowing them from another teacher, and then when I moved from Westminster, he said, "Give me my best." Fair enough. Even I had them for like 4 years, but I couldn't be like the government and just keep them. This is pretty common. All right, so that is all. Awesome. We finished chapter 6.